Hi, welcome to the eChem channel. This is Veronica. Today I would like to introduce to you our recently published paper from my group at Katrin, Palacký University Olomouc, Czech Republic. This paper reports novel nitrogen-doped graphene and its application in the energy storage field. But first, some background. As we all know, the demands for energy storage are growing with increasing electromobility, availability of mobile devices, and so on. Therefore, the development of electrochemical energy storage devices with improved performance, safety, eco-friendliness, and lower cost is essential. Carbon-based supercapacitors are fulfilling these demands compared to lithium-based systems, since they offer also metal independence and long life cycle. Graphene, as one of the members of the carbon family, has many advantages, and therefore it is promising material for supercapacitors. So in this work, we were able to increase the energy content which is stored per volumetric unit of supercapacitors using graphene derivative. The outline of this presentation is very brief. First, I would like to show you the synthesis process, following by the characterization of this novel material, and finally the electrochemical testing and benchmarking. Our novel material is synthesized via wet chemistry approach. We exfoliated the fluorographite, which is used industrially as a lubricant, therefore it is widely available precursor, in organic liquid phase, and then we use the sodium azide as a nitrogen source. The azide anion initiated the reaction by nucleophilic attack on carbon radical defects, leading to nitrogen release and fluorine elimination. As the final product, we get the nitrogen-doped graphene, denoted as GN3, with superdoping of 16 atomic percent of nitrogen. Next, we did the characterization on our material. The Raman spectrum is showing large presence of sp3 carbons, including the non-healable defects and the vacancies, and also a fair number of aromatic areas. Following, the atomic concentrations of the GN3 final product consists of 16 atomic percent of nitrogen, only 1.5 atomic percent of fluorine, and 79 atomic percent of carbon. Solid-state NMR revealed non-functionalized and non-nitrogen bonded sp3 carbon atoms, which are formed gradually as the reaction progressed at 154 ppm. Moreover, from the FTIR, we can clearly see the decrease of carbon-fluorine band as the reaction progresses, and emerging aromatic band again as the reaction progresses. Moreover, the theoretical model of GN3 structural fragment, which was optimized by first principles spin-polarized DFT calculations, showing the carbon-bearing radicals which were forming the interlayer bonds, which are here highlighted in spheres. Here, we can see that the GN3 sheets are really homogeneously and densely covered with nitrogen doping. What is also extraordinary about the GN3 material is its very high mass density of 2.8 gram per cubic centimeter compared to only 0.5 gram per cubic centimeter before pressing. The BET surface area yielded 150 square meters per gram, and the methylene blue sorption yielded the surface area of 300 square meters per gram. Here, from the thickness measurements which we performed using SEM and also digital micrometer, we optimized the pressing test and also the paste composition to consistently reach 2.7 to 2.8 gram per cubic centimeter compared to already mentioned around 0.5 gram per cubic centimeter before pressing. Here is the overview of all of the pressing tests we are showing in the paper. So we are showing the bare aluminum foil, the GN3 material on aluminum foil, both of the commercial available car mods, and then the high mass loading. First, control tests were done with aluminum foil by itself. The results verified that no compression took place for this aluminum foil. Moreover, we also performed control tests with commercial carbons of high surface area, around 2000 square meters per gram, with the porous carbon and the Corare carbon, which is used commercially for supercapacitors. Their densities match those which are provided by the supplier. Moreover, we were also able to press the GN3 material at high loading to confirm that our material can be pressed to this high density even at the high loading. And now for the EChem testing. The CVs exhibit quasi-rectangular shape, which is retained even at higher scan rates, with only minor redox peaks, which are coming from the nitrogen functionalities. The rate test of symmetrical GN3 cell using the ionic liquid as an electrolyte showed 76% capacitance retention at even 40 ampere per gram current density. For benchmarking, the carbons, the porous carbon and the curare carbon, which were already mentioned and tested as a control test during the pressing, were evaluated under identical conditions. The GN3, as visible here, had significantly better discharging time than the porous carbon and the curare carbon, and its performance was superior in both volumetric and gravimetric terms, which is impressive given the dramatic difference in the material's bed surface areas. The energy density is the Achilles heel of supercapacitors, whereas the high power densities are one of their greatest strengths. The GN3 cell demonstrated groundbreaking performance by delivering both ultra-high energy and power density. And to set these results into the context of the current state of the art, they are presented alongside the best literature data on top-performing materials. When making these comparisons, we made sure that the same sets of equations and metrics were used in all of the cases. And indeed, as you can see, the GN3 material performed much better, almost twice better than the best example from the literature. I would like to also mention that the GN3 material is patent protected with the European patent, and we also filed the PCT application. The next plans for the GN3 material are prototype supercapacitor assembly of two types of supercapacitor cells, evaluation and possible commercialization. We would like to also explore other possible applications of the GN3 material, not only in the energy storage field. Thank you very much for your kind attention. If you have any questions, just leave us some comments. The videos in our EChem channel are free and are only for educational purposes and knowledge distribution. Subscribe, like our videos, and it will certainly motivate us to go further. Thank you again for watching the video, and see you next time!